So now we're going to look at the chemical properties of the halogens, right? The group 17 elements, as well as the chemical properties of the halides, which are the anions that the halogens form. Okay, so starting with the halogens, right? So we're going to look at chlorine, bromine, and iodine, right? Now the halogens are oxidizing agents. Okay, they're oxidizing agents because they undergo reduction. They gain electrons. Okay, so they're oxidizing agents. Okay, they're oxidizing agents because they gain electrons, right, to form the halides, right, which are the anions. So we have Cl minus, right, we have Br minus, and then we have I minus, right. So the halogens are oxidizing agents because they undergo reduction, causing other things to get oxidized, right. When we react them with other things, they cause other things to undergo oxidation. They themselves undergo reduction. So we can say that the halogens are oxidizing agents. Halogens are oxidizing agents. The oxidizing strength of the halogens decreases as we go down the group. So for example, iodine is a weaker oxidizing agent than chlorine. Okay, and the reason why is because down the group, right? The reason why is because down the group the number of shells increases, right? And as the number of shells increases, right? As the number of shells increases, the nucleus is trying to attract that incoming electron. Remember, the halogens want to gain, they want to gain electrons, right? And down the group, as the number of shells increases, shielding increases, radius increases, right? The incoming electron experiences weaker nuclear attraction. It's harder to gain an electron as we go down the group, right? Weaker nuclear attraction towards the incoming electron, right? As the number of shells is increasing, radius is increasing, shielding is increasing, right? Which means that weaker attraction means that the tendency to gain electrons decreases down the group, right? Tendency to gain electrons decreases. So we can say that the oxidizing strength, okay, the oxidizing strength decreases down the group. Okay. Decreases down the group. And the reason why is because, as we just said, the number of shells increases. The number of shells increases. If the number of shells increases, we know that the shielding increases, right? And atomic radius also increases. So we can say therefore shielding, right, of the valence electrons, right, or the valence electrons are more shielded from the nucleus, right? So shielding and atomic radius increase down the group, right? Increase down the group. So we can say hence, right, the incoming electron experiences weaker nuclear attraction, right? Experiences weaker nuclear attraction. Experiences weaker nuclear attraction, right, as we go down the group, right? And therefore we can say, hence we can say that the tendency to gain electrons decreases, right? Tendency to gain electrons decreases, right? So they don't gain electrons as readily as we go down the group. And of course, when we talk about the tendency to gain electrons, right, we're saying the tendency to undergo reduction decreases, right? So they're weaker oxidizing agents down the group, right? Gain of electrons refers to reduction. So the halogens themselves are oxidizing agents, right, in their elemental form, right? But their anions, which are called the halides, okay, the halides are reducing agents, okay? Halides are reducing agents, okay, reducing agents. And we can see that over here, right, from these equations, we can see that the halides are reducing agents because they undergo oxidation, right? They lose electrons, they undergo oxidation, and they are reducing agents. And As far as their reducing strength is concerned, okay, it increases down the group. It's the exact opposite, right? As we go down the group and the atoms get larger, it's harder to gain electrons, right? So the oxidizing strength of the halogens decreases down the group. But obviously, as the size of the ions increases, right, as the size of the ions increases, it's easier to lose electrons. So the strength of halides as reducing agents increases down the group. So we can say that the reducing strength of the halides, reducing strength, right, increases down the group. Reducing strength increases down the group. And we have the same explanation, right? But here we're talking about the ionic radius. So down the group, the number of shells increases, right? The number of shells increases, right? Which means that, therefore, we can say that the shielding and ionic radius increase, right? Shielding and ionic radius increase as we go down the group. Hence, the valence electrons experience weaker nuclear attraction. Okay, experience weaker nuclear attraction, which means that, therefore, we can say that the tendency to lose electrons for the anions, for these anions, increases as we go down the group, right? So tendency to lose electrons increases, right? Which means that they undergo oxidation more easily, which means that they're better reducing agents as we go down the group, right? Because loss of electrons refers to oxidation. Right? Another thing to note here is that oxidizing agents may also be referred to as oxidants. Okay, oxidants. So if we say something is an oxidizing agent, right, it's the same thing as saying it's an oxidant. Okay. Similarly, reducing agents may also be referred to as reductants. So any reducing agent may be referred to as a reductant. So the halogens are oxidants, right? The half equation for their reduction is the forward reaction here, right? And the halides are reductants, and the half equations for their oxidation is the backward reaction. So let's look at displacement reactions that highlight the relative oxidizing strength of the halogens and the relative reducing strength of the halides. Okay, so we're looking at displacement reactions. Right. So the first displacement reaction that we're going to look at is the reaction of chlorine with sodium iodide. So we can say that this reaction will take place, and the reason why this reaction will take place is because chlorine is more reactive than iodine. So the formation of the chloride ion is more favorable than the formation of the iodide ion from the respective halogens, right? So we can say that the formation of chloride is more favorable. Similarly, we can say that iodide is more reactive than chloride, so we can say that the formation of the halogen from the halide is more favorable for iodine. So as far as halogens are concerned, chlorine is more reactive than iodine. As far as halides are concerned, iodide is more reactive than chloride. So therefore, a reaction will take place between these two, okay, and chlorine will displace iodine from the salt. So we'll form iodine plus sodium chloride. Okay, over here, the halogen is your oxidizing agent and the halide is the reducing agent. This can be referred to as a displacement reaction, but it is a redox reaction, right? Because again, the halogen itself is undergoing reduction and the halide is undergoing oxidation. So the halogen is the oxidant or the oxidizing agent and the halide is the reductant or the reducing agent. We can also write down the ionic equation for this, right? As far as the ionic equation is concerned, right, we have Cl2 reacting with iodide, right? So I minus to form iodine and chloride. Right? The sodium ions are just spectator ions in this. The next reaction that we're going to look at is the reaction between iodine and sodium chloride, right, which is the reverse reaction here. Now, will this reaction occur? Now, this reaction won't take place. And the reason why is because iodine is a weaker oxidizing agent than chlorine. Iodine is a weaker oxidizing agent than chlorine, or we can say that chloride is a weaker reducing agent than iodide, right? So you have the weaker oxidizing agent in the halogen, and you have the weaker reducing agent in the halide. So they won't react with each other, right? Iodine and sodium chloride won't react with each other. All right. Similarly, if we were to say, will bromine react with sodium iodide? Bromine will react with sodium iodide again because bromine is a better oxidizing agent than iodine, and iodide is a better reducing agent than bromide, right? So again, we'll have a displacement reaction where bromine will displace iodine, right, from the salt. So we're going to have iodine plus sodium bromide. And we have 2NaI and 2NaBr. Right, and the ionic equation for this, right, the ionic equation for this is the following, right? This is the ionic equation. We can say that Br2 will react with iodide ions to form iodine and bromide ions, right? And again, the halide is the reducing agent. It undergoes oxidation, right? Oxidation number increases from -1 to 0, right? Or it loses electrons. And the halogen is the oxidizing agent. It undergoes reduction, right? Oxidation number decreases from 0 to -1, or we can say that it gains electrons. Last reaction, the question is, will bromine react with chloride ions? Again, this reaction won't take place because bromine is a weaker oxidizing agent than chlorine, or we can say that chloride is a weaker reducing agent than bromide. Okay, so you're not going to see any reaction here. Okay, the salts for these reactions that we use, the halide salts, are either potassium salts or sodium salts. Okay, so here we use the sodium salts. We can also use the potassium salts. Okay, so we can use potassium iodide instead of sodium iodide as well. Those are the two commonly used salts for these reactions. So when we talk about displacement reaction, we talk about the halogens reacting with the halides, right? We have chlorine, bromine, and iodine reacting with chloride, bromide, and iodide, right? So over here, right, the question is, will chlorine be able to displace bromide and iodide? The answer is yes. Chlorine will be able to oxidize bromide and iodide because it's the most reactive of the three halogens. Bromine, on the other hand, will not be able to displace chloride. Okay, it won't be able to oxidize chloride because bromine is a weaker oxidizing agent than chlorine, right? So it won't react with chloride, but it will be able to displace iodide, right? So it will be able to oxidize iodide to iodine because bromine is more reactive than iodine. Since iodine is the weakest of the three oxidizing agents, okay, it won't be able to oxidize chloride or bromide, right? So it won't be able to displace chloride or bromide, right? So from this table, we can clearly see that chlorine is the strongest oxidizing agent since it can displace both bromide and iodide, right? And we can also see, if we look at the columns, right, we can see that iodide is the strongest reducing agent. It can reduce both chlorine and bromine. Okay, so chlorine will oxidize bromide and iodide, bromine will only oxidize iodide, and iodine won't be able to oxidize chloride or bromide. So looking at the rows, we can see that chlorine is the strongest oxidizing agent, and similarly we can see chloride won't be able to reduce bromine or iodine, right? It's the weakest of the three reducing agent. Bromide will only reduce chlorine, right? And then iodide will reduce both chlorine and bromine. So it's the strongest of the three reducing agents. So now we're going to look at the reactions of the halogens with hydrogen. Okay, the reactions of halogens, okay, with hydrogen to form hydrogen halides. Okay, to form hydrogen halides. One thing to note here is that all of these reactions are exothermic. Okay, so when halogens react with hydrogen to form hydrogen halides, okay, we get exothermic reactions. At least for the reactions we're going to be looking at. Okay, we're going to be looking at the reactions with chlorine, bromine, and iodine. Okay, each of these three reactions are going to be exothermic. So the first reaction that we have is when chlorine reacts with hydrogen. Okay, and here again we have chlorine gas reacting with hydrogen gas. Okay, and we form hydrogen chloride. Okay, we form hydrogen chloride, which is a gas. A common mistake is that people will call this hydrochloric acid. Okay, in the aqueous form, when HCl dissolves in water to form an aqueous solution of HCl, that's referred to as hydrochloric acid. Okay, but the gas is referred to as hydrogen chloride. Okay, so this is a hydrogen halide. So this is an explosive reaction. Okay, this is an explosive reaction. Okay, when the reactants are exposed to UV light. Okay, so just in the presence of light, okay, chlorine will react with hydrogen in an explosive manner. Okay, it will be highly exothermic. Okay, when chlorine and hydrogen are exposed to UV light. On the other hand, if we look at the reaction of bromine with hydrogen, right? Bromine we know is less reactive than chlorine, so it doesn't react as explosively. Okay, it's a much slower reaction. All right, normally when we want to react bromine with hydrogen, we're also going to provide heat. We're also going to provide heat. Okay, so here we can say that this reaction is a fairly slow reaction. It's a fairly slow reaction when heated. Notice that in this reaction, we're reacting bromine in its gaseous form with hydrogen to form hydrogen bromide, okay, which is also a gas. And then lastly, we have the reaction with iodine, right? The reaction of hydrogen with iodine. Okay, in this reaction, right, iodine, again in the vapor form, okay, we're going to react gaseous iodine with hydrogen. Okay, and this is a reversible reaction. It's the least favorable of the three reactions, since iodine is the least reactive of the three halogens that we've listed here, right? And we're going to form hydrogen iodide. Okay, again, this is a gas, okay, and this is a reversible reaction when heated, right? So it's the least favorable of the three reactions. A reversible reaction when heated. I'll just write down the names, right? HCl is referred to as hydrogen chloride. Okay, HCl gas is hydrogen chloride. HBr gas is hydrogen bromide. Okay, and then HI is hydrogen iodide. Now these reactions become less exothermic down the group. Okay, so the reaction between hydrogen, okay, and the halogens becomes less exothermic down the group. Okay, reactions become less exothermic down the group. Right, and this trend can be explained in terms of bond energies. So if we take a look at these bond energies here, right? Take a look at these bond energies. What we see is, right? What we see is this, right? We can clearly see that as we go down the group, right, the bond energy decreases, right? So we can look at the bond energies of the Cl-Cl bond, the Br-Br bond, and the I-I bond, right? These are the bonds that we're breaking, right? And then the bonds that we're forming are the hydrogen and halogen bonds, right, which are HCl, HBr, and HI. And again, we can see that down the group that bond energy is decreasing. Okay. Now the other thing that we observe, the other thing to observe here is that we can see that the hydrogen halogen bonds are much stronger than the halogen halogen bonds. This is because of the very small size of the hydrogen atom, right? These bonds, the HCl bond, for example, is much stronger than the Cl-Cl bond. The HBr bond is much stronger than the Br-Br bond, right? And the HI bond is much stronger than the II bond, right? So if you look at the reactions, for example, if you look at the reaction of chlorine with hydrogen, right? In all three cases, obviously, we're breaking the bond between the hydrogen atoms in a hydrogen molecule. But if you look at this reaction, right, we're breaking 1 mole of Cl-Cl bonds, and we're forming 2 moles of HCl bonds. So for every 1 bond that we break in the halogen, we want we form 2 moles of the hydrogen halogen bond. And we know that the bond formation, right, the bond formation between the hydrogen and the halogen releases energy, right? And there's going to be a significant amount of energy, right? And again, we're forming 2 moles of this for every 1 mole of this that's breaking. So this isn't playing as significant a role because it's much smaller in energy and it's only 1 mole of this breaking. Whereas the formation of this, much higher energy, and we have 2 moles, the formation of this determines how exothermic the reaction is, really, right? And we can see that the HCl bond is much stronger than the HBr bond, which is stronger than the HI bond, right? So we can say that this reaction becomes less exothermic down the group because lesser energy is being released when the hydrogen halogen bond forms. Okay, so this is because the formation of HCl will release the most energy, followed by HBr, followed by HI. Lesser the amount of energy released, the less exothermic the reaction. So over here we can say that the reactions become less exothermic down the group, okay, and the reason why is because the HX bond, right, becomes weaker down the group. Okay, so the HX bond becomes weaker down the group, and this is because as we go down the group, right, the number of shells increases, right, down the group, right, the number of shells increases, right, which means that number of shells increases and therefore the atomic radius and shielding increase, right? What that means is that, right, hence we know that the bond length increases and the bond energy decreases. Bond length increases and bond energy decreases. So bond energy decreases. All right, and if the bond energy is decreasing, we can say therefore lesser energy is released in the formation of the hydrogen halogen bond. Okay, so that is the HX bond. Here X refers to halogens. So in the formation of the HX bond. So we know that exothermic reactions are more favorable, right, generally speaking. So this reaction will be the most exothermic. So if we, the reason why this reaction is the most favorable is twofold. First reason is that chlorine is the best oxidizing agent, and secondly, the reaction is the most exothermic. So if we had to explain why this is the most favorable reaction, we would talk about why chlorine is the best oxidizing agent. For the reaction of iodine with hydrogen, on the other hand, right, we would explain why iodine is the weakest of the 3 oxidizing agents, and this reaction is the least exothermic, and therefore this will be the least favorable reaction. So now we're going to look at the thermal decomposition of the hydrogen halides. Okay, thermal decomposition of hydrogen halides. Okay, thermal decomposition of hydrogen halides. The thermal decomposition of the hydrogen halide is the reverse reaction of what we've just seen, right? In this, what we're going to do is we're going to take, for example, something like HCl. Okay, we're going to heat it to form back hydrogen and chlorine. Now, the decomposition of HCl, okay, doesn't take place. Okay, you can decompose HCl, but it requires a very, very high temperature, above 500 degrees Celsius. So in a lab, you won't be able to decompose HCl. Okay, and this again can be explained by the fact that the HCl bond is the strongest. On the other hand, when we talk about the decomposition of HBr, okay, this does take place more readily, but you have partial decomposition, okay, to form hydrogen and bromine. And again, you're heating this, okay, so you're going to see bromine produced in its vapor form. Okay, this reaction is more favorable because the HBr bond is relatively weaker compared to the HCl bond. Okay, so it breaks more easily. All right, and what you're going to observe here is that you're going to see. So what you're going to observe here is you're going to see a slightly orange, okay, slightly orange or brown vapor. So that's the bromine vapor that's forming. Right, and the reason you see a slight color is because you have partial decomposition. Okay, you have partial decomposition, not complete. On the other hand, hydrogen iodide will decompose the most easily. Okay, hydrogen iodide will decompose the most easily because the bond between hydrogen and iodine is the weakest of the three hydrogen halides. Okay, and in this case, we're going to form hydrogen again and iodine vapor. Okay, and the observation here will be that we're going to see purple vapor, right? Form. And you're going to see a fairly dark purple color because you'll have almost complete decomposition. So what we can say here is that the thermal stability, okay, the thermal stability of the hydrogen halides decreases down the group. Okay, they're less resistant to heat. They decompose more easily down the group. Okay, the thermal stability decreases down the group. And again, this can be explained by the fact that the strength of the HX bond decreases, right? The bond energy decreases. So HX bond energy decreases down the group, right? And again, we have the exact same thing, okay? As the number of shells increases, we can say that radius and shielding increase down the group, right? Which means that therefore bond length increases, right? Bond length increases, right? And the attraction between the nuclei and the shared pair of electrons, right, becomes weaker. Right, that's just a covalent bond, right? Covalent bond is attraction between nuclei and shared pair of electrons. This attraction becomes weaker, which means that the bonds are weaker down the group. So the bond energy is decreasing down the group. So because the bond energy is decreasing, hence a lower temperature is needed for decomposition. Now the hydrogen halides, okay, HCl, okay, HBr, and HI, okay, okay, they all, their appearance can be described as white misty fumes. Okay, they look like steam basically. You know, when we have steam coming out on a cold day, right? That's what they look like. So they're actually colorless, but they appear white because they're fairly dense. Okay, so their appearance can be described as white steamy fumes or white misty fumes. And one more thing to note is that, okay, that they form, okay, the hydrogen halides, okay, okay, dissolve in water, to form acidic solutions. Okay. So when HCl gas dissolves in water, we get HCl aqueous, which is hydrochloric acid. When HBr gas dissolves in water, we get hydrobromic acid. Again, when HI dissolves in water, we get HI aqueous, which is hydroiodic acid.